Okay, so the goal of this video is to show you an application of the ratio test. This is probably one of the most useful tests that we can do. So basically, I'm going to show you, okay, basically using the same reference as before, p equals the limit of n to infinity of u of n plus 1 over un. So basically this is just saying the n plus 1th term divided by the nth term, and find the limit as n approaches infinity of that, right? And then what it's saying is that whatever that limit is, that's what p is. So if that limit is less than 1, then the series converges. If it's greater than 1, then the series diverges. And if it's equal to 1, then no test, meaning it's inconclusive, okay? So basically, let's apply this, okay? So again, this is one of the most important tests. So I wanted to continue on with the harmonic series. One moment, let's see. Oh yeah, no, let's do a geometric series, okay? So basically, the series is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. It's basically, if you look at this, you see that there's a pattern of 1 over n squared, right? So, actually, one moment. This is actually a p series, okay? Yeah. A p series. Okay, but so wait, this is wrong. So because this is a p series, basically when the p is greater than 1, it converges. So because we have p is equal to 2, this series converges, okay? So again, a p series looks like something like this: 1 over n to the p, right? So the point is that because the p is equal to 2, the series converges. So, but if we wanted to, I want to show you so therefore, using the p series test, basically we know that this converges, but I wanted to try using the ratio test and see what happens. So basically we have using the ratio test, right? P is equal to the limit of n approaching infinity of u of n plus 1 term over the un term, and it's the absolute value, right? So I forgot to show that up there actually. Let me just fix that right here. This should be the absolute value. So basically, right, what we're doing is the limit as n approaches infinity of, again, this is 1 over n squared, right? So 1 over n plus 1 squared divided by 1 over n squared. So basically all we did is we took the general term, and anywhere that there's an n, we substitute in an n plus 1. It's really just that. And you divide. And I showed it like this, but basically when you divide by a fraction, you can multiply by the reciprocal. Thus, this right here is equal to the limit as n approaches infinity of 1 over n plus 1 squared times n squared over 1. Because remember, 1 over n squared is, the reciprocal of that is n squared divided by 1. Now, what you should notice is, when I just simplified this and I got the limit of n to infinity of n squared over, and then basically this term right here I expanded out to n squared plus 2n plus 1. Okay. Now, if you remember, you can use L'Hopital's rule and get the limit of n approaches infinity of 2n divided by 2n plus 2. Okay? And then you can apply L'Hopital's rule again, and you get basically the limit of n approaching infinity of 2 over 2, which is equal to 1. Okay? Which, according to the ratio test, right, P equal 1 means that it's inconclusive. So basically what we showed is that even though we have this ratio test, sometimes it's inconclusive, and therefore that's why using that P test was just much simpler and much faster. Okay? So I guess what I could say is, if you recognize a P-type series, you should use the P-test rather than some other test, because it's just more convenient. Okay? Okay, let's move on. Thank you.